Happy learning! Today we're going to talk about shortest paths. All right, so if you've been watching along these last few weeks, you would know that so far we've only focused on routes that go through an entire graph. So that go through a graph with the objective of visiting all edges. That's what we did originally. And then recently we looked at visiting all vertices. Okay, but today we're going to look at a slightly different type of problem. We're going to try to get from one vertex to another as quickly as possible. Okay, so our goal is to find a shortest path on a weighted graph. Right? This is what your GPS does every time you ask for directions. It tries to get you from where you are to where you're going as quickly as possible. All right, we're going to use an algorithm known as Dijkstra's algorithm to solve this problem. All right, and with Dijkstra's algorithm, we are going to label not the edges. The edges already will have labels because it's a weighted graph. We're going to label the vertices with 2 bits of information. Okay, so each vertex will be given a 2-part label. Okay, we're going to call it L of V. So that's the label of this vertex V. And it's going to have 2 components. It's going to have some other vertex, which I'll denote by X for now, and some weight associated with V. All right, so far we've only seen weights associated with edges, but there's no reason why we can't associate weights with V. X will be the vertex used to travel to V. It's going to be the vertex we just visited. And the weight of our vertex will be the total weight needed to get to that vertex so far. So it's the weight of the path that was used to get to V. All right, so when we do this algorithm, we're going to have all of our edges are going to be labeled with the weights, and then all of our vertices are going to get these labels that update throughout the problem. Okay? And so let's write down Dijkstra's algorithm, and then we'll walk through an example. And I'll try to do it slowly, but the nice thing about YouTube is if I go too fast, put it on 0.75 speed. Get me in slow motion. All right. So we're going to walk through Dijkstra's algorithm. This is an incredibly famous algorithm in the history of computer science. It's one of the first algorithms, or might be the first algorithm, to solve this shortest path problem. Okay, so what do we need? Our input is a weighted, connected, simple graph. Okay, so remember, connected means we could somehow get from one vertex to another. Simple means that there's no multi-edges and there's no loops. And we also need some additional information. We need to know where we're starting and where we're going. Okay, so wherever we're starting, that's our start vertex. And wherever we'd like to end up, that's our end vertex. Okay, so suppose you live in Washington, D.C., and you want to drive to New York City, put it in your GPS. Start would be D.C., end would be New York City. All right? So the first step is we're going to assign some initial labels to the vertices. Okay, so for each vertex, we're going to set L of x equal to dash 0 if x is the starting vertex, or L of x equals dash infinity otherwise. Okay, so our first step is to each of the vertices, we're going to label the start dash 0. Everything else is going to be dash infinity. Okay, step 2. We're going to, let's let u be the start, and we're going to let f be the neighbors of u. All right, so these are the edges that we could travel to initially. What we're going to do is we're going to update the labels of f in the following way. So we're going to update the labels for each v in f as follows. Okay, so if the weight of u plus the weight of the edge uv is less than the weight of v, we're going to update the label of v. Okay, and so we're going to update the label of v saying we came from u, and our new weight is going to be the weight of u plus the weight of the edge uv. Okay, if this inequality does not hold, so if the weight of v is less than or equal to this sum here, then we're not going to update the label at all. Okay, our next step, this step 2 is kind of the main idea here. The next step is we're going to look at our graph, and we'll do an example. So just bear with me while we're writing this down. Our next step is to look at all of the vertices. We want to highlight the vertex. with the lowest weight. And the edge UV, so this is the edge, used to update the weight. Okay, so let's say V is this edge with the lowest weight, or is the vertex with the lowest weight. We're going to highlight it and the edge used to get there. And we're going to redefine basically we're going to set U equal to V, and then we're going to loop through and do step 2 again. All right, so step 4 is repeat 2 and 3. Okay, and then step 5 is we look at end and we just read the labels and it tells us how to get to the end. Okay, so the shortest path is found by tracing back from end using the first component of the label. Okay, and if we run through this algorithm, the output is the shortest path from start to end with total weight given by the weight of the end vertex. Okay, this might feel very overwhelming at this point, and that's okay. We're going to do an example right now. We'll walk through this algorithm, and we're going to see it's really not too bad. Okay? So bear with me. So let me erase this, and we will work through Dijkstra's algorithm. Okay, I know that was a lot of writing. All right, so we're going to apply Dijkstra's algorithm with start equal to the vertex G and end equal to the vertex C. All right, and let me give you the graph. All right, here's our graph. A, B, C, D, E, F, and G. So we're going to go from G to C, and the weights are 9, 1, 1, 2, 6, 5, 1, 8, 6, and 5. All right. So our goal is to get from G to C as quickly as possible. All right. So let me erase this. We're going to need some space. But you'll see, hopefully, by the end of this example, that this algorithm is not that difficult. All right, so what was the first step? The first step was to get our initial labels. The label for G, that's our start, is going to be dash 0. And all of the other labels are dash infinity. Okay, so now we're at G. So we typically use the letter U to represent where we're at. So U is G. The neighbors of U, which we called capital F, are A and F. Okay, so for each of these, A and F, we need a check. So we'll start with A. Is it the case that the weight of G plus the weight of AG, is this less than the weight of A? All right, so this is literally, we have to just check. So weight of G is 0. Weight of AG is 9. Is this less than the weight of A? Infinity. Okay, let me know in the comments. Is 9 less than infinity? Yes. All right, great. It is. So now we're going to update the label for A. It's no longer dash infinity. It is now G 9. Okay, where did the 9 come from? It came from this here. 9. We have to do this with our entire F set. So now we'll go to our next vertex, F. We need to check, is the weight of G plus the weight of FG less than the weight of F? The weight of G, of course, is 0. The weight of FG, that's this edge, it's 1. Is it the case that 0 plus 1 is less than infinity? Yes. Okay, so we update the label from dash infinity to G1. Okay? Now our final step before we cycle through again is now we want to look at our graph. Of all the vertices we haven't been to yet, which has the least weight? Okay? And it's F. The weight of F is 1, which is smaller than 9 and smaller than all the infinities. So now U equals F. All right? Now we want to look to the vertices, the neighbors of F that haven't been highlighted yet. And we're going to do the same process that we just did. All right, so the neighbors of F that haven't been highlighted are A, B, D, and E. And so for each of these 4, we have to check, is the weight of F plus the weight of the edge less than the vertices, the vertices weight. All right, so we'll do it for all 4. We want to check, is the weight of F plus the weight of AF or FA, is this less than the weight of A? The weight of F is 1. The weight of AF or FA is also 1. So is 1 plus 1 less than 9? Yes. Okay, we update A. We update A's label. It is now F. One plus 1 is 2. Okay, with B, D, and E, they all have weights of infinity. Okay, so it's going to be very similar to what we did up here. So I'm going to kind of go a little bit quicker here. We're going to check the weight of F, which is 1, plus the weight of the edge. 1 plus 2, is that less than infinity? Yes. So that's F3. Why 3? 1 plus 2. With D, is 1 plus 1 less than infinity? Yes. 1 plus 1 is 2. So we go F, 2. And with E, is 1 plus 8 less than infinity? Yes. So we do F9. Right? The 9 is 1 plus 8. All right? Now we look. So far we've done here, here, and we traveled along this edge. We need to find the vertex with the smallest label. 2, 3, infinity, 2, 9. 2 and 2, those are the smallest. We have to pick one of them. It doesn't matter which one we pick first because we'll get to the next one second. So I'll do A first. All right, so U is A, and the neighbors of A that haven't been highlighted yet, so we're here now. The neighbors of A that haven't been highlighted yet is just B. There's only one of them. So this one will actually be pretty quick. All right, we need to check, is the weight of A plus the weight of AB, is that less than the weight of B? Weight of A is 2. Weight of AB is 6. Is that less than the weight of B, which is 3? 2 plus 6 is 8. 8 is not less than 3. We do not update the weight of B. Okay? You see that? Since 8 is not less than 3, we do not update B. All right, and then we've gone through the whole F set, so we're done with this step. We now look at our graph, find the vertex with the lowest label that hasn't been highlighted. That's D. Okay? So we're going to highlight D. How did we get to D? We got there from F. So we're going to highlight this edge as well. All right, so U equals D. The neighbors of D that haven't been highlighted are E and C. Finally, we got the C. That's where we're trying to get to. So C and E. All right, so let's do each of these. C, we don't really have to write out the steps. Since it has this label of infinity, we know we're going to do D7, right? 2 plus 5 is 7. But let's check for E. So is the weight of D plus the weight of DE, is that less than the weight of E? 2 plus 6, is that less than 9? Yes. Okay, so we update this label to D, and not 9 anymore, but 8. All right, now what do? We look at our graph. we find the vertex with the smallest label that hasn't been highlighted yet. And then we're going to highlight it. That's B. All right, and so probably just do it here. The only unhighlighted neighbor of B is C. All right, so we need to check. Is the weight of B plus the weight of BC, is that less than the weight of C? Weight of B is 3. Weight of BC is 5. Is that less than 7? 3 plus 5 is 8. 8 is not less than 7, so we do not update the label. We've gone through our entire F set, so it's time to highlight. The vertex with the smallest label is C. We highlight it, and the edge used to get there, this one. And we finally made it to end. And so we can record our shortest path. So what is the shortest path? Well, we know its length is going to be 7. Okay, so the label next to the C tells us what the length of the shortest path is. And how do we get it? Well, we know it ends at C. We came from D. D came from F. And F came from G. All right, so this is the shortest way to get from G to C on this graph. I know it felt like a pain in the butt working through all these steps, but you could imagine a computer could do this instantly, right? Which you see it when you type in, when you use your GPS. Okay? So yeah, I hope you found this video helpful. Dijkstra's algorithm is awesome for finding the shortest path, and it gives us the weight, which is really cool as well. Let me know in the comments if you have any thoughts or concerns, or if you've ever used Dijkstra's algorithm. Now you know its name. Yeah, I'll see you next time. Bye-bye.